In this video, I'm going to walk through a complete supervised learning example using linear regression. I'm using the classic MPG dataset, which basically shows the fuel consumption in mile per gallon. This data set contains information about cars, things like horsepower, weight, engine size, fuel efficiency, stuff like that. And then I basically use a linear regression to train the data and basically predict MPG for newer car. But before reaching this point, I already performed some exploratory data analysis on the data, which is always the first step that you need to do on your data. Um, and by that, I inspected the data set, cleaned it, transformed it, visualized the relationship um, through univariate and bivariate analysis. I finished that by looking at coloration matrix, which shows the relationships between different input features and MPGs. Always higher coloration is more useful because it helps us identify which features might be good predictors in our model. I'm not going to go over the full EDA, exploratory data analysis, again, since it was covered in a different section, but here are the key takeaways from the data. Heavier, more powerful cars with larger engines tend to have lower MPG. Newer cars basically tend to have higher MPG. Fewer cylinders in cars often means better fuel efficiency. Cars from some regions show higher average MPG, and the correlation matrix also was confirmed. Several of those relationships visually. Basically, these insights gives us a solid information and intuition before we move into building our prediction model. It actually shows us which features of the data are gonna help us more in predicting what we're supposed to predict. Okay, now let's move on to our actual topic. Um, Now I'm ready. Basically, now when the data is ready and it's clean and ready to use, um, we are going to use that to train a supervised learning model that predicts MPGs. Um, First, I chose a few features that seems useful for prediction, like weight, horsepower, displacements, and model year. I selected these because earlier in my EDA, these features kind of showed relationships with MPG. Probably there are better features you can use. For example, acceleration also had high coloration. But this is just an example, and for this example, I just kept things simple. Just remember that in real world, you always want to choose the most informative features of the data to guarantee you're going to end up with a good model. Probably I'm not doing that here. Probably I should have added acceleration here, but I'm just leave it for you in case you want to also add that to the data, see if your result is going to change a little bit. So I'm just going to pick like some general features from the data. And the target variables are the thing that I want to predict, like basically the MPGs that I want to predict. So these are the results that we kind of want to predict. We just call them target data or target variables. And then I perform like here I perform like a train test split. This is like a general step and a crucial step in supervised learning. The idea is that the training set is the portion of the data that the model is allowed to learn from. The testing set, and it's going to be held aside to basically simulate the brand new unseen data that we're going to use eventually to test our model, to see if our using these test sets, using this test data, can actually our model can predict acceptable results. We basically just do this to get an honest estimate of how well a model performs on a data that basically it has never seen before. In this notebook, I kind of use like 80-20 split. Usually that's something everybody does, 80% for training, 20% for testing. I also set a random seed to the split, everything, so it's going to be reproducible, all these data and everything. And as you can see, after the split, I checked the shapes of the training and test sets to confirm that everything worked properly. Once the data was split, I basically created a linear regression model from the scikit-learn library. At this point, this model hasn't learned anything yet. It's just empty model waiting to be trained. To train it, I called the fit method and passed in the training features and the training targets. This is where the learning actually happens. But let me explain what the fit function does. The fit function contains the entire training process. It tries to basically learn the best mathematical relationship between the input features, and the target MPG values. For linear regression, the relationship gonna look like a straight line formula. So here's a formula, and this is how we kind of interpret it. We start with this W0, which is basically the intercept point where everything should start, and then some weight, and multiply by x1 could be like the weight of the car, plus and some weight again, with multiplied by the horsepower of the car. So these x's are different features of the data, like the weight of the car, horsepower of the car, displacements or model year of the car. And these weights are the coefficients and the parameters that basically we adjust to make sure we can fit the data in a mathematical functions. Basically, the fit method finds the values of those weights that make the model's prediction as close as possible to true MPG values in the training data. Under the hood, scikit-learn uses the method called normal equation, which computes the best fitting line. Well, you might ask what the normal equation is and everything and how it works. We don't really need to know about how this fit method can achieve such a thing, and what type of mathematical operation it uses behind the scene. It's not going to be covered in this module, but overall, if you're interested in like what type of mathematic it uses under the hood, I added some detailed mathematical details here, in case you're curious to know how it actually can come up with a good weight for each one of those input features, which basically uses this normal equation to basically minimizes the value for each weight. So basically, this fit method, this fit function or fit method, is the learning step, is a training step. It adjusts the weights so the model matches the training data, as well as it can, basically. After training, I inspected I inspected the learned weights and the intercept value. The intercept is basically the baseline prediction when all features are zero, basically where we need to start. And these some of these weights are, as you can see, are positive, meaning they increase MPG. Some are negative, meaning they decrease MPG. Each weight tells us how the predicted MPG basically changes when that feature increases by 1 unit, while the others stay the same. For example, if the weight of the car is negative, that means heavier the car is, um, it will predict the lower MPG, which should make sense. Um, you can manually adjust these weights to kind of enforce different behaviors, but that belongs to a more advanced topic. Like in case you're not getting good results, you can come back here and play with these weights to basically adjust and make your model even better. Um, what does the score function do? Basically, the next thing that I'm doing here is that I evaluated the model using this score function or method. So basically, for linear regression, this method returns the R squared value. R squared value answers the question of how much of the variation in MPGs can this model explain. So basically, the maximum is going to be 1, which is like a perfect prediction. As we get closer to 0, that means this is as good as predicting like the average MPG every time. So it's not pretty good. And then if it gets a negative, that means it's worse than predicting the average. So if you see R squared of 0.79 here, that means model explains about 79% of variation in MPGs, and the remaining 21% is due to noises, I don't know, missing information, or not using a good model, or model limitations. Um, this is not talking about accuracy. This is talks about the variation. Okay, sometimes we define models, and then the way we evaluate them, we just look at the percentage of the accuracy. Like for classification models, is this a spam email or not? So we want to know the percentage of the accuracy this model can predict. For example, like it can predict 99% of emails as a spam. But here for the regression, we're not using accuracy. We're using R squared, which basically tells us like how much the variation of MPG um, can be explained in this model. So it's kind of, they are a little different. Basically, this number gives us the high level sense of how useful our model is. We can also compute 3 additional evaluation metrics like MAE. Basically predicts the average size of prediction mistakes. Lower is always better. MSE, mean square error, basically it's the average squared error, mainly useful mathematically. Lower is always better. And RMSE, the typical size of prediction error, also in MPG unit, which is also, if it's lower, is better. There are different, but R2 is the commonly used ones. Again, all of these helps to interpret the model in real world terms. For example, if the RMSE is around 3.6 mpg, that means on average our predictions are off by around 3 to 4 miles per gallon, something like that. And here, after everything, after using that score to evaluate the model, we kind of want to study to see how well actually um, we basically want to visualize everything to actually see how the model is working. Um, Basically, I uh, drew this plot, and in this plot, each point represents one car. The x-axis is the correct MPG. The y-axis is the predicted MPG, and this diagonal line represents basically like the perfect like relationship between the actual MPG and predicted, or I should say the perfect prediction. This diagonal line basically shows the perfect prediction here, where predicted MPGs are equal to actual MPGs or true MPGs. A good model produces points that cluster close, very close to that diagonal line. The poor model would produce like points that are widely scattered, curved, or unrelated to this diagonal line. This plot visually confirms whether the model is capturing the overall trend in the data and making reasonably accurate predictions on unseen cars. Just read the comments and the details. I'm sure it will make sense, like how things are done. And finally, I use a single test example to show how close the model's prediction is to a real world value, to real world MPG value. In this example, the true MPG was 26, and the model predicted 25.90, which is not bad. It's quite close. And for context, honestly, here's what typical values should look like in real world regression tasks. Like the good R2 is around like 0.6 to 0.8, which is what we got here. Pretty good R2 is around like 0.8 to 0.9, and like an excellent R2 is above 0.9. Which is kind of rare in like all these messy real world data that we have, but that could happen. If that happens, that means you have a pretty good model here. And here is my overall summary here. That basically this is basically what I've done here. I prepared the MPG dataset with essential cleaning steps. I selected a few features and split the data into training and testing. I trained the linear regression model, and basically I kind of went over what the training or fit, and what the score or evaluation one methods or functions actually do. I kind of evaluated the model using R squared, and I also talked about MAE, MSE, and RMSE, which are like other ways of evaluating the regression, and eventually we visualized the true vs predicted MPG to assess the model performance. So this notebook should give you kind of like an end-to-end example of supervised learning with linear regression, starting from raw data all the way to interpreting the prediction. So this should give you a good idea of what the supervised learning is, what the process is, how we can use scikit-learn, and how you can actually use our model to predict and visualize things. Thanks for watching.